Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 5, Increasing and Decreasing Functions. Okay, example 1, nonlinear functions in the real world. Not all real-world situations can be modeled by linear functions. Okay? There are times when nonlinear function is needed to describe the relationship between two types of quantities. Compare these two scenarios. So we have scenario A and we have scenario B here. All right, let me change the view so we can see both at the same time. Okay, here we go. Aleph is running at a constant rate on a flat paved road. The graph below represents the total distance he covers with respect to time. So if I come along here and I see that this is an integer, it's right on a corner, and I continue, this is an integer and it's right on a corner, then I can determine rise and run to get the rate of change. So from 2 to 4 is 2, and from 15 to 30 is 15. So rise over run is 2/15, which means for every 15 minutes, he can run 2 miles. Or for every 2 miles, it takes him 15 minutes, either way you want to word it. So this is a linear function. It is constant. So then if I took this rise over run and move it anywhere on the graph, you'll see that it never changes. It matches everywhere. Okay, part B, though, says Shannon is running on a flat, rocky trail that eventually rises up a steep mountain. So obviously, she's running at a fast rate here, but then her rate is gradually decreasing over time. So if I drew a line, let's use a ruler for this, by the way, and I'm going to just show you what's happening here with a segment that would represent our rate of change. So if I were to draw a line from the origin where she started, and if it was constant, then she's going at a pretty decent clip like this, okay? But obviously, if I move that, it's getting flatter and flatter as she goes from here. So it was way down here, it was right on that line, but then all of a sudden she broke away. So what happened was that her rate decreased, and therefore the slope decreased, the rate of change decreased like this. And then as we went further, it decreased even more, and then as we got way out here, she's really slowing down. So this is her rate way back here. So that kind of lines up right there. But if I bring this down here, then that would mean she'd have only gone over 30 minutes, she'd have only gone 1 mile. But in the first, it only took her 5 minutes, a little more than 5 minutes to go a mile. So she is definitely slowing down. And that's what I wanted to point out to you there with this line. Okay, so as it gets steeper, obviously it gets harder to run up a hill. She's slowing down as she continues. And that is the difference. So she started out quickly, but then began slowing down and getting challenged by the elevation. Okay, exercises 1 and 2. In your own words, describe what is happening as Aleph is running during the following intervals of time, 0 and 15 minutes. So if I go back, Aleph is this first one. So between 0 and 15 minutes is right here. So what's happening is he's running at a constant rate. Okay, he's running, or he runs, and I could say he started at 0, so how far did he run? He runs in the first 15 minutes 2 miles. He runs 2 miles. At a constant rate. From 15 to 30, 15 he's at 2, 30 he's at 4, he ran 2 miles. So he ran, or he runs 2 miles again. 30 to 45 minutes, if I go back and look, here's 30 right here, here's 45 right here, He, again, if I just move this, it will show you that he went up 2, 4 to 6, and from 30 to 45 is 15. Okay, so he's going up 2 over 15. So that's still a constant rate. So he runs 2 miles. He still runs another 2 miles. And then from 45 to 60 minutes, well, again, if I take this here and move it to the 45-minute mark and over to the 60, he rose 2 and went 15. So he went another 2 miles in this 15 minutes. So again, he runs 2 miles. So as you can see, from 0 to 15, he ran 2 miles. From 15 to 30, 2 miles. 30 to 45, 2 miles. 45 to 60, 2 miles. Therefore, throughout the whole duration of his run, he was running at a constant rate of 2 miles for every 15 minutes. So if I wrote the unit of measurement, I guess I'd put 2 miles in 15 minutes. Number 2, in your own words, describe what Sharon is doing. At 0 to 15, what did she do? Or Shannon. Shannon, from 0 to 15 is right here. She ran 1.5 miles. Okay, so in 0 to 15 minutes, she ran 1.5 miles. 15 to 30 minutes, 15 to 30 minutes is now from here to here, and she went from 1.5 miles to about 2.25. And 1.5 miles to 2.25 is, she ran approximately 3/4 of a mile. And then 30 to 45 minutes, from here, from 30 to 45, it looks like she went 2.25 to 3.25. That's about 1 mile. Is that right? No, that's 2.25, and this is 2.5. So a little more than 2.5. So she ran approximately, I don't know, 1/4 mile from 30 to 45 minutes. And then 45 to 60, went the wrong way again. From 45 to 60, 45 is here, 60 is here. She went from a little more than 2.5 to 3, and that looks like, I don't know, maybe approximately 4/10 of a mile, 0.4 miles. Okay, so obviously she's slowing down, and that might have been more than 1/4 of a mile, because this is 4/10 of a mile, which is just under a half, and that's probably between a half and 3/4. So this is probably off, so maybe like 3/5, which is 60%, 75%, 60%, 40%. Okay, that's about right. Okay, so obviously you can see she's slowing down. Approximately 0.4 or 4/10 of a mile. Example 2. The rate of change of a function can provide useful information about the relationship between two quantities. A linear function has a constant rate of change. A nonlinear function has a variable rate of change. So this is linear, and it's increasing at a constant rate. This is nonlinear, increasing at a variable rate. This is linear, decreasing at a constant rate. And this is a nonlinear function, decreasing at a variable rate. A linear function with a constant rate is this, 1, 2, 3, 4. We added 1 to each. We're adding 3 to each, so the rate of change is increasing by 3 on the y every time x increases by 1. Remember, your rate of change is y over x, which would be 3 over 1, or simply 3. A nonlinear function, since this is increasing by 1, this is increasing by 2, then it increased by 2 again, but then it increased by 4, and then it increased by 8. So that is a variable rate of change. Exercises 3 and 5. Number 3 says, different breeds of dogs have different growth rates. A large breed dog typically experiences a rapid growth rate from birth to age 6 months. At that point, the growth rate begins to slow down until the dog reaches full growth around 2 years of age. Sketch a graph that represents the weight of a large breed dog from birth to 2 years of age. Okay, so in order for me to sketch this, I have to take into consideration that they said the dog experiences a rapid growth rate from birth to age 6 months. So from birth to 6 months, it's a rapid growth. So I'd probably want this to probably be about here. And then after 24 months, it's rapid up to here, but then it tapers off and then maybe ends up in the 70s. So maybe it gains like 50 pounds the first 6 months and then only another 25 pounds over the next 18 months. So in order to graph that, I guess we could come up like this. And it's a rapid growth, but then all of a sudden it starts to slow down and the dog begins to grow at a slower rate until it reaches 2 years of age. So that'd be rapid and decreasing. Is the function represented by the graph linear or nonlinear? It is nonlinear because it has a variable rate of change. And is not a graph of a line. C says, is the function represented by the graph increasing or decreasing? Explain. It is increasing. And my explanation is, I would say, as age in months increases, the weight of the dog increases. Okay, number 4. It says Nika took her laptop to school and drained the battery while typing a research paper. When she returned home, she connected her laptop to a power source and the battery recharged at a constant rate. Sketch a graph that represents the battery charge with respect to time. So we're just talking about when she returned home. So time and hours, she returns home and then she's going to charge it. So the battery's drained, it's dead. And then after an hour, maybe it's 20%. And then after 2 hours, 40%. 3 hours, 60%. 4 hours, 80%. So maybe it didn't fully charge after that. And then if I graph this, and I use a straight edge always, and I draw a line from my first point, and it's always most accurate to pick a point further away to draw your line. So there is the graph of the charging of her laptop. It is linear because it charged at a constant rate. Remember, rate is as we increase, or as time and hours increases, the battery charge increases as well. So if I drew this, okay, so if I draw this after 1 hour, the battery life increased by 20%. If I move this up, it didn't change. If I move it up, it's still the same. And if I move it up, it's still the same. So it changed at a constant rate. Part C says, is the function represented by the graph increasing or decreasing? Well, it is increasing because as time increases, the battery charge percent increases. That's what you would write. As time increases, battery charge percent increased. Okay, so as one increased, so did the other. Number 5, the long jump is a track and field event where an athlete attempts to leap as far as possible from a given point. Mike Powell of the United States set the long jump world record of 8.95 meters, which is 29.4 feet during the 91 World Championships in Tokyo, Japan. Sketch the graph that represents the path of a high school athlete attempting the long jump. Length of jump in meters, height of jump in meters. So he jumped 8.95 meters. So let's just graph. This guy's the world record, and it says to sketch a graph that represents the path of a high school athlete, not this guy. So this guy made it out to here. Here's 8, here's 9. 8.95 is approximately there. So he jumped from here over to here. I would not expect a high school athlete to break or match the world record. So let's say he jumps not as far. Let's say he jumps, I don't know, 6 feet. So if he jumps 6 feet, well, how far off the ground in meters? Well, that's 1 meter is 3 feet, 2 meters is 6 feet. So let's just say he jumped off the ground maybe 4 feet, a little more than a meter, and it would probably peak right about here. So picture this guy running and jumping, and he jumps off the ground, and gravity takes over, and then he starts coming back down to the surface of the earth, and there he is. That would look like through the air from a side view of a person jumping 6 meters. Is the function represented by the graph linear or nonlinear? It's obviously nonlinear. Okay. For starters, it increases to a point, a maximum point, and then it decreases. So it is nonlinear. That is not at a constant rate. Okay. So when you first jump, your elevation increases quickly, but then as you can see, it's slowing down. And if I did that with a graph of a line like so, then I move this line over here, obviously the rate is slowing. So if I drew the slope here, then you see that it's slowing, and then eventually when I move it over here, it actually gets to a point where it's decreasing. So I went from increasing to decreasing. So therefore, definitely not linear. Part C, is the function represented increasing or decreasing? It is increasing, then decreasing. So the graph is increasing and then decreasing. So it is increasing until the 3 meter mark, then it decreases. Okay, example 3, a Ferris wheel. Lamar and his sister are riding a Ferris wheel at a state fair. Using their watches, they find that it takes 8 seconds for the Ferris wheel to make a complete revolution. The graph below represents Lamar and his sister's distance above the ground with respect to time. So picture a Ferris wheel. You're down at the bottom, you just get in it, and it starts to rotate. So the Ferris wheel's like this. So you get in this basket right here, okay, and then it starts to rotate this way. Well, as it rotates, you are going up. You're going up, you are going up until you get here. So that would be this distance here. So they're going up in elevation until they got to the top of the Ferris wheel, and then they start to come back down around to where they began. And that is this decreasing distance here. And then now we're back down at the bottom where they got on, same elevation. And it repeats over and over and over. Okay. That is called a sinusoidal function, if you want to know the term, but that's future math classes. So it says Lamar and his sister are riding a Ferris wheel. The graph below represents their distance above the ground. Exercise 6 through 9 says use the graph, for example 3, to answer the following questions. A, is the function represented by the graph linear or nonlinear? It is definitely nonlinear. Where is the function increasing? Well, it increases from 0 to approximately 8 seconds. And then it is increasing again from about, actually that's not 0 to 8 seconds, that's 5, so that's about 4. Let's call that 4 seconds. So it's increasing from 0 to 4 seconds. It is increasing from, that looks like about 7 seconds, to, this is a little more than 10, let's call it 12. So it's increasing from 7 to 12 seconds, and then it's increasing. So really what I'm going to do is I'm going to copy these colors over. Okay, so now I've color coded the whole thing. Hopefully you can see the green is where it's increasing and the red is where it's decreasing. So I'm answering the question, where is the function increasing? From 0 to 4 seconds, which is right here. And then it's increasing again from 7 until 12 seconds, and then it increases again. This is 15, so that's about 16 to 20 seconds. And then it's increasing from 24 to, I don't know, 27. And it's increasing from about 32 or 33 to 36, I would say. That is where it's increasing. Where is the function decreasing? The function is decreasing wherever there's red. So it's decreasing from these points in between. So it's decreasing from 4 to 7 seconds. It is decreasing from 12 to 16 seconds. And it's decreasing from 20 to 24 seconds. And it's decreasing from 27 to 33 seconds. Okay, so there you have it. Number 7, how high above the ground is the platform for passengers to get on the Ferris wheel? Explain your reasoning. So now they're asking, where are we getting on the thing? Well, obviously you get on at the bottom, so that the lowest level, and that is right here. And that is at 5 feet. Okay, so we get on right there at 5 feet off the ground. So the platform is 5 feet off the ground. Number 8 says, based on the graph, how many revolutions does the Ferris wheel complete during the 40-second interval? So if I go back here, I color-coded them. Increasing then decreasing is 1 full rotation, as I showed here. So this is 1, 2, 3, 4, 5 in 40 seconds. So it is 5 revolutions. Number 9 says, what is the diameter of the Ferris wheel? Okay, so now we have to decide what the diameter of the Ferris wheel is. Well, diameter is distance from the top to the bottom going through the center by definition. That is a diameter. So a diameter is the maximum minus the minimum. And the maximum is 45 feet and the minimum is 5. So the diameter is maximum elevation minus the minimum elevation. And the maximum elevation was 45 feet minus the minimum, which was 5 feet. So the diameter of the Ferris wheel is 40 feet. Okay, that is the end of Lesson 5. Review the lesson summary and go do your problem set.